Rows of data. Here's the Python program that we'll write. We're going to try and go through this data and do some operation that we know is very slow, grouped weighted summary statistics. We'll group them by that category, and then we'll take a look at what the weighted mean would look like. So when I think about writing some Python code, I am not hesitant to make use of things like the data classes.dataclass, collections.nametuple, enum.enum, because often I'm thinking about two separate domains existing in my Python code. The first domain is the program structuring domain, and the second domain is the computational domain. In the computational domain, what I'm doing is some raw, performance-sensitive computation. In the program structuring domain, what I'm doing is expressing my intentionality, which is usually done in a performance-insensitive way. And typically, when I'm talking about program structuring, I'm talking about pure Python code. When I'm talking about computational work, I'm talking about code within a restricted computation domain, like NumPy's ND array or a pandas data frame or pandas series. For the program structuring, I want to use all of the features of Python, all of the dynamic features of Python, and I'm not going to worry that much because generally the program structuring, by virtue of needing to be human understandable, is going to be quite minimal in scope over the computational work. In fact, I should expect that the computational work will be the source of all of the time spent in the program will be in the computational work. Whereas in the program structuring, it might be slow, but these little micro-optimizations won't really benefit me much because they'll be overwhelmed by the speed of the computational work. So to show you what that really means, let's think. Program structuring is describing to somebody what the problem I'm trying to solve is. So the problem I'm trying to solve is load a bunch of data files and do a data analysis of these and give a result to the screen. So to load a bunch of data files, well, I figure out where those data files are located. And I can do something like this. Here, each path for the paths that I have, if the path suffix equals .pkl. And let's make sure our data directory existed. That's good. Oh, and this needs to be mapped into our VRAP, so let's get that done as well. So here we'll do one small thing just to make that available for our use, which requires getting that available in our environment. So here we'll bind Okay, so here we go. So hopefully that gives us our data directory. Very good. And then hopefully we should see this in our environment as well. There we go. So those are all our data files. If I need to skip these, I might put these into a Python set. So I might say, you know what, let's eliminate some of these data files. Maybe for whatever reason, I don't want to work on any of the files that have certain names. So I might do something like this. And I might use things like the Python set, which I know are going to be faster at operations, like removing elements or identifying if elements are in this structure. But for the most part, my concern here is, can somebody read this code and understand what's happening? And for the most part, I can. You know, find all the pkl files, mark that this file won't be processed, and here we could say all data files. And the ones that we process are all the data files minus the excluded data files. Now, one important thing that is missing from this discussion of the program structuring versus the computational is, even though we typically set this up as a dichotomy, it's actually a spectrum. It's very much the case that your program structuring is at one end of the spectrum, and your computational work is at the other end of the spectrum. And it is very clear what you do when you're at the ends of the spectrum, here, you just use pure Python, and you don't worry that much. On the other side, you use NumPy, or pandas, or another restricted computation domain, and you obey whatever the restrictions are of that domain. But it's not that uncommon to find yourself somewhere in the middle of the spectrum, where the work is both computational in nature, but also some kind of program structuring, or where the work is actually performance sensitive despite being program structuring. Here, in this case, we'll see an example of that. That is to say, when we have, say, a NumPy and D array or a pandas data frame, we know that it's very expensive for us to concatenate that. So we're actually going to have to do something in the pure Python domain that might otherwise be something that we actually want to do inside the restricted computation domain. For example, we might actually need to do our read pickle operation in a Python loop, even though you can think that this is going to happen on the scope of the number of data files that we have, which might genuinely be very many. Here there's only 100, but we could easily imagine there could be 100,000, in which case we will actually see this code be a performance issue in our pure Python side, even though, otherwise we might consider it to be program structuring. And in fact, in a case like this, we actually run into some difficulty trying to figure out, well, how do we address the slowness of some Python code that's also interacting with very fast NumPy or pandas code? Here, naively, my approach for solving a problem like this is to focus on what is most understandable and what's most readable first and foremost. So I would first do something like the following. I am more concerned about the correctness of this code initially than I am about the speed of this code. So I'm much more interested in having a loop comprehension here that gives me the ability to identify what the data files were and what was read from those data files than necessarily making this a little bit faster. When I want to turn this into one large piece of data, again, I'm going to focus on what I need to do to get that done, but I'm not going to worry too much about performance. So here, this would just be a concat, and we're actually going to do a little bit more work here than just a normal concat. We're going to say this would be this is a data frame for each one of these in our raw data.items. And we can see from the speed of this code, it's not particularly fast. Just that data loading is actually quite slow to get our 100,000 or so, or sorry, our 10 million or so lines of data. Here you can see I haven't really sweated it that much because I focused more on being able to say, which line or which data file did this particular line come from, so that, for example, if there's something wrong in the data file, I can sort this out. Something like this starts to get problematic because I need to measure this to figure out, is this really where the slowness of this code is? And part of the problem is the slowness of this code may be at a level that I don't really have the ability to touch. That is to say, what if it's the case that some third-party library is where the slowness of my code exists, say the pandas concat? Am I really going to dive into pandas and speed that up on a whim? Probably not. In general, when I think about writing faster Python code, my other guidance is this. Try to isolate the places where you anticipate there is slowness so that you can actually surgically improve the speed of that code. And so it may not be the case that I might not be able to go into concat and speed it up in the case where you have something that looks like this, but it may be the case that somebody else can do that, or it may be the case that I can make my life a little bit easier by doing something like write a helper function here, like this, and moving this operation into this helper function at what will overall be a slowdown in the code because I have one more function call, but not a material slowdown in the code. And here we'll say, this is concat our data. And of course, really getting this to be as flexible as we want it to be is going to be a little bit tricky, but in the interim, if we've identified that it always looks like this pattern, then later on I can figure out how to lower this into the restricted computation domain. Largely what I'm looking at doing is figuring out places where I can isolate the computational behavior in my code, even if it might appear to be part of the program structuring, and then later on lower it. Because it could very well be the case that I spot that one of these lines of code is very slow, and as a consequence of spotting that that line of code is very slow, I rewrite it then and there, but then I never revisit that. When I never revisit that, I don't know, after I've upgraded all of the moving parts that exist at the levels below the code that I wrote, whether the performance improvement I had is still a performance improvement or it's become a performance degradation. And I never really know, oh, hold on a second, I made that fast over here, then I made it slower, let me go fix it. But are all the places where I made this change things that I have to fix later? And so part of isolating this gives me the ability to add in some performance improvements later and figuring out what structurally I can do in order to improve this. In this case, is there anything I could structurally do? Well, I'm avoiding whatever the index-aligned concatenation is, and that might actually be something that at one point I want to avoid. For example, I could later on discover that it may be a reset index and then a set index. Might speed this up overall. And it would be very nice for me to be able to spot that in, and let's do concat data. Be very nice for me to spot this in one place and then to be able to apply that performance improvement across all the places in my code where I have done this. So here you can see I have at least my data loaded up, and you can see here maybe this reset index, set index wasn't the best thing for me to do. Maybe if I do I really don't want to do that. But I could drop down to NumPy or something like that to get this to be just a little bit faster. Okay, let's see if we can get this going. Very good. I picked this specific example because this specific example is a case where the generality of our restricted computation domains is not sufficient to allow us to just say, oh, yeah, leave it to NumPy, leave it to pandas to speed this up. It is the case that for the most part in our Python code, if that Python code is program structuring, we don't really worry about these micro benchmarks too much. But that's not the whole story. Let me show you. I know that if I want to do a group by the category value, and let's make sure that this is named in our original data, just so that we get this right. So here, this needs to be a rename axis, and we'll just print out one of these. Otherwise, the naming when we load this up will be missing. Yeah, perfect. Here, if we want to group by that category, and we want to do a weighted average, we know we have to do that with an apply, so we can look at two columns, and we can see that once we do this with apply with the user-defined function, since those categories are very small, we're actually going to be dropped down to the speed of pure Python. It is genuinely the case that even if your work is predominantly in NumPy or pandas, the improvements being made in Python 3.11 and 3.12 will benefit you, because anything that we can do to reduce the number of Python function calls that we have or to speed up a Python function call will, in general, speed up our code, where we need the flexibility of a user-defined function. And so here, I do something like this. I'll multiply the weights times the values, and then we sum this, and we divide this by the sum of the weights. And what we'll discover is this is just going to be very, 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 very slow. The high cardinality grouped weighted summary statistic is very slow as a consequence of having to call this Python function many, many, many times, and as the slowness of the index-aligned concatenation with the dot apply.